In this lecture, we will discuss about the phasor representation, which is one of the important concept used in electrical systems to represent the alternating quantities. So this lecture will discuss about the introduction to the phasors. What is a phasor basically? How do we represent the AC quantities with phasor? And we will understand a little bit about phasor addition and phasor subtraction. Now, what is a phasor? Or before that, we should understand the representation of the alternating voltage and current. Now, till now, if you have gone through the previous lectures, till now we have represented the AC quantities through the waveform. Like if we talk about some AC current or AC voltage, so a sinusoidal AC current or a sinusoidal AC voltage is represented through a waveform basically like this. So this is a waveform representation of the alternating quantity, wherein we have a peak value, we have some RMS value of this, we have some average value of this, then we have the instantaneous value of course, right? So this is one way of representing the alternating voltage and alternating current. Then another way of representing the instantaneous value of alternating voltage and current is this. We represent these quantities through some m sine omega t, or the current is represented as it is equal to Im sine omega t. So this is the mathematical representation of the alternating current and voltage. Now, there is one more way to represent the voltage and current, because if you see the sinusoidal voltage has, it is basically signal which is varying with respect to time. It is changing its phase at every moment. A phase is basically, it is uh, having the different magnitude at different angle or different point of time, which we call as the phasor representation of the alternating quantity. The alternating quantities are represented with the help of a line basically, which is nothing but an arrow. This arrow represents two things basically. One is the magnitude of the AC signal, and second is the direction of the AC signal. As you see here, this particular quantity has magnitude as well as direction. So instead of representing the AC signal with this waveform or the equation, we have one more representation which is given by line and arrowhead basically. So line and arrow represent. So this is what we call as a phasor basically. So phasor is basically not just a line, it is a way of representing. However, phasor is a rotating line, it is a rotating vector basically. So it is a vector which rotates at a particular velocity in a particular direction. So it is assumed to be rotating in the anti-clockwise direction, right? So if you see here, this is represented with the help of a diagram here. So this red arrow, it represents, it is a phasor basically, which is representing some alternating quantity, any alternating quantity, let it be voltage or current. So it is rotating with an angular velocity of omega in anti-clockwise direction. So when it completes its one cycle, it generates one cycle of sine wave. Okay, so this can be understood by, uh, you know, uh, uh, backtracking the whole process. So if you uh, take a phasor basically, which is, let us say, at some point of time is lying horizontally. So if you draw the sine wave through the phasor, which will rotate in anti-clockwise with some speed omega. So when it is horizontal with the time axis, so its value is 0. When it moves to a certain angle theta 1 or phi 1, for example, or theta 1, so now its value will change. Now from here we will see this theta 1, because this is theta, and we will draw the line where these two lines coincide. That is the magnitude of this phasor at this point theta 1. And then it moves, let us say, some point theta 2, some angle theta 2. So here we'll draw a horizontal line from the tip of the phasor, and we'll have theta 2 value on the time axis. Let us say this is theta 2. We'll draw a horizontal, vertical line here. So where these 2 points coincide, this is the magnitude. So these are the magnitudes basically, and this is the phase. Theta 1 is the phase here. This is the phase. This is magnitude. This is the magnitude, right? Now that means a phasor has magnitude as well as phase. Phase means you can say a direction, or its value at certain point of time in space, right? So similarly, when it will keep on changing its angular position in space, its value will keep on changing here also. So ultimately, you will get, when you will join all these points, you will get a sine wave. You'll get a sine wave. So that means a rotating vector, which is also known as phasor, produces a sinusoidal signal. So, uh, if we summarize the phasor, phasor is a it is a rotating vector. It has some angular velocity, and it rotates in anti-clockwise direction. However, this anti-clockwise direction is also a convention basically. So it can also rotate in clockwise direction, but generally when we deal with the angles, if you relate it with the trigonometry. So in trigonometry you have four quadrants basically. So this is first quadrant, which is from 0 to 90 degrees, then from 90 to 180 degrees, and from 180 to 270 degrees, and from 270 to back to 0 or 360 degrees. This is one complete cycle. So when we deal with the quadrants, we generally go like this. So phasor is also assumed to be rotating in anti-clockwise direction, and because it's changing its angular position every time. So when you're moving from in anti-clockwise direction, your angle is increasing basically. So you're increasing from 0 degree to 90, then 180, then 270, then 360, and at 360 you have one complete cycle, right? So from there we can relate the movement of phasor in anti-clockwise direction, and it is rotating with some angular velocity omega here, right? Now you can understand the whole process with the help of this diagram, which is shown here. You can see that this arrow basically represents some alternating quantity. Okay, it may be alternating voltage, it may be alternating current. Now when this arrow, which is a phasor, which is a rotating vector, is at 0 degrees. Now 0 degree is with respect to the time axis, or you can say theta. This is the x-axis, which may be omega t or theta, right? So when it is at 0, so if you project a line from here, so it would be intersecting with the origin, so its value is 0 here, means the magnitude at this point, the magnitude and phase, it is 0, and phase is also 0. Now phase means its angle with respect to the 0 axis basically. So it is 0. With respect to 0, it is 0. Okay. So now when it moves at 30 degree with respect to this 0 degree, it has moved, or it has shifted, or it has displaced angular, it has the angular displacement of 30 degree in anti-clockwise direction. So now if you project a line from here and you shift, you take 30 degree, from 0 you come to 30 degree, and you draw a line like this, so the intersection point will be this one. So this is the magnitude, this is the magnitude of this phasor at theta is equal to 30 degree. So theta is equal to 30 degree is basically the phasor, right? Now similarly, if when it moves to 60 degree like this, and we project a line from here, and then we project a line from theta is equal to 60 degree vertically, so this intersection point will give the magnitude and phase of this phasor at theta is equal to 60 degree. So in this way we will get certain points like this, and when we join all these points, we'll get a sine wave. So that means any rotating vector rotating with some angular velocity will produces a sine wave. So this is what we get from the phasor of an alternating quantity. So this is one way of representing basically. So from the discussion till now, we have uh, understood that a phasor is basically uh, a way of representing the alternating quantity. A phasor is represented with an arrow, with a line basically, with an arrow. So a line with an arrow. Arrow represents the direction and line represents the magnitude, right? Phasor is nothing but a rotating vector. It rotates with some angular velocity omega, and it rotates in anti-clockwise direction, which is just a convention. You can relate it with the trigonometry, right? So from the discussion till now related to phasor, we can note down the following points which are important as far as your phasors are concerned. The first point is that the length of the phasor represents the maximum value, and the angle with axis of reference represents the phase, or indicates the phase of the alternating quantity, right? Like, what does it mean? It means that if you have a phasor, like this is the reference line, this is the x-axis, okay, this is the reference line. With respect to this reference, if your phasor is is positioned here, if it is lying here in space, and the angle with reference line is theta, okay, so uh, the length of this would represent the magnitude, and this would represent the phase of the alternating quantity. So this is what we were discussing, right? Now the phasor representation enables us to quickly obtain the numerical values and at the same time have a picture before the eye of the event taking place in the circuit. So basically, phasor gives a more convenient way of understanding the alternating signals. Okay, if we have a phasor like this, and we have a reference line here, which is some angle theta 1, so we can easily find out its magnitude and we can easily find out its phase. So if we have multiple phasors with us, we can easily analyze them as compared to the waveform representation. Okay, so this is more convenient way of representing the alternating quantity. So phasors can be added and subtracted more conveniently, more easily. You can have a phasor addition and phasor subtraction. Phasor of an AC quantity is represented with a line with an arrowhead. Okay, so this is what we were discussing. It is a line with an arrow. The arrow of the phasor represents the direction, and length of the line represents the magnitude of the AC quantity. So this length represents the magnitude of the AC quantity, and the arrow represents the direction. So this is what we were discussing, and we can easily represent the multiple AC quantities with the help of phasors. So this arrow, like, it represents some phasor. It is a phasor basically which represents some alternating quantity. Okay, so phasor diagram. So we may have multiple phasors also. We may have two phasors. We may have three phasors depending upon the number of alternating quantities, right? Like in three-phase systems. In three-phase systems, we represent three voltages with three phasors which are, uh, kept at 120 degree from each other, right? So phasor diagrams are basically to represent the magnitude and direction relationship between two or more alternating quantities graphic. So this is the graphical way of representing the alternating quantities. Now we will elaborate our discussion with the help of this diagram here. So this is the same thing which we discussed in previous slides. If you see, if you have a phasor, a vector basically, this is a vector here, this one, which represents some current. So Im is basically the maximum value of this particular phasor, which is represented by the length of the phasor, like this, and the arrow represents the direction. So if you project, like at some point of time, t1, your phasor is lying at this position in space here. It is lying here in space. Now the angle which it makes with the reference line, which is this one, is theta. So theta would become its phase, right? So if you project a line from here and you take theta from zero, from origin you take theta angle, and you project a line vertically from here, so that this is the magnitude and phase of this particular phasor. So this is what we discussed in previous slides. Now we can represent the multiple sine waves or multiple AC quantities with the help of phasors. Like in this example, in this diagram, if you see, we have two you know alternating quantities. One is the voltage, which is V is equal to Vm sine omega t. So this is the voltage, means this V represents the instantaneous value of voltage, and this represents the peak value or maximum value, right? Now, the second one is the current I. Okay, so I is the instantaneous value. Okay, so this is I is equal to Im sine. Now, what we will write here, that you need to understand, we will not write omega t just. Now, if you see, this phasor is basically phi radius behind. So here your I is 5 radians or degrees behind the voltage. So we call it as the lag. That is, current is lagging V by 5 radians or 5 degrees, whatever. Right? So this is what we call as lag. What does it mean? It means that the current will start its zero 5 radians after the voltage started its zero. right? It is a kind of relay race. Okay, if you have a track, so just imagine a track. Okay, so you have the athletes positioned like this. So you have the another batch of athletes here. So if they run in this direction with same velocity and their velocity remains same, their speed remains same, so they all will have the same difference. They will all will have the same gap between them, and similarly they will pass on the same thing. Okay, so the further the athletes will have the same gap. Okay, so it is just like that. Means the two athletes are running on a track with the same gap. So this gap we call as phase difference. This is what we call as phase difference. The difference in their phases. Now, if you see here, the voltage, it's coinciding with the horizontal axis. It is coinciding here. So at this point of time, the value of voltage is zero and its phase is also zero. But the current is behind the voltage, means phi radius behind. So we will go phi radius back here, like here. Okay, so we'll go here and we'll see this 5 degrees or 5 radians, and means our current will start from this particular point. Otherwise we can also say that if this rotates and it moves to 5 degrees ahead, if the voltage rotates and it moves 5 degrees in anti-clockwise, so this current will come to zero position, right? This current will come to zero position. So this means that the zero of this current will start 5 degrees after the zero of voltage. If the zero voltage has started from here, the zero of current will start from 5 degrees later. Okay, so this is how we can represent the more number of alternating signals with the help of phasors. Like in this, we will write V, the instantaneous value, as Vm sine omega t, and the current as Im sine omega t minus phi. So this negative sign indicates that this current is lagging the voltage by phi radians. So the phase difference in these two is phi. We can also represent it in this way. Like this can also be represented if you take current at x-axis and you take voltage at some phi radians ahead. So this we call that V is leading I by phi radians or degrees, right? So this can also be written or represented. So the equations will become here: V is equal to Vm sine omega t plus phi, and I is I am sine omega t. So we'll say that voltage is leading current by 5 degrees or 5 radians. However, in both the cases, this one and this one, in both the cases, the phase difference will remain phi itself. Okay, so if we have to draw the waveform in this case, so let us take the second case where current is here. So this is Im, and the voltage is, let us say, some 5 degrees or 5 radians ahead. So if you draw a waveform, this is the x-axis, omega t. So the current will be here, okay, and the voltage will start from this point after 5. So we will take the 5 radians from here. Not, will not go to this side 5 radians, we will go um, because here the voltage is advanced. Basically advanced means it is starting ahead of this one. So your current will start like this, and your voltage will start from here. which is 5 degrees. So it will start like this. So you can see your voltage has completed its one cycle 5 degrees before the current. Okay, or you can say the current has completed its one cycle 5 degrees after the voltage. So this is what we say call as lead or lag. So lead or lag is nothing but it is in relation with one reference signal. Here we are taking current as a reference, and here we are taking voltage as a reference, right? So this is how we can represent the phase. So this is what we call as phase difference. Basically, this phi is the phase difference, right? Now here is some animation given just for your understanding. You can see here this one, the first one, a phasor is rotating in anti-clockwise direction. So if you plot all the points of this phasor in space in a two dimension here with x-axis and y-axis, you'll get a sine wave. And here you can see there are two phasors, blue line and red line. So these two phasors are rotating in anti-clockwise direction with the same velocity. Means their gap will remain same throughout the rotation. So you can see the blue line, because it is ahead of the red line, or blue arrow is ahead of the red arrow. So sine wave is completing first as compared to red. Now here the speed is kept a bit slow in this one. Speed is kept a bit slow. So you can see the phasor is rotating in anti-clockwise, and the every point, every value here, every value, this one is plotted here, and you will get a sine wave. And then this one also you can see this is in opposite direction, this is in this direction. Both are same. Like here if you see when your phasor it has 0, so you have 0 value. When it moves to 30 degree, like it moves to 30 degree, this is the magnitude, then this magnitude, and it is moving. So we are plotting the values basically of this phasor at every instant in space, right? So this is how we get the sinusoidal waveforms basically. You can also relate this rotating phasor with the rotating coil. If you we have if you talk about the a generator basically, wherein we have a coil which rotates in anti-clockwise direction with some angular velocity omega. So we will get an EMF basically in case we have the slip rings, right, instead of split rings. So this EMF would be a sinusoidal EMF basically, which we obtain. So you can simply think of that coil is rotating in the magnetic field in anti-clockwise direction with some angular velocity, and it is generating a sinusoidal signal, a sinusoidal alternating voltage and alternating current, right? Now let us come to the addition of the alternating quantities. So the alternating quantities, or which are represented with the help of phasors, can be added with the help of a famous method which we call as parallelogram method or parallelogram law of factor addition. So in parallelogram law of factor addition, we take two phasors, like here Im2 and Im1 are two phasors, wherein Im2 is leading. So always remember one thing, that lead and lag is always understood in anti-clockwise direction. Like if we have two things, like here, let us say this is some quantity x and this is some quantity y. So we'll say that x is leading y. Okay, x is leading y by some angle, let us say phi, for example. Or you can also say that y is lagging x by phi. So both statements are true. Okay, so here if you see Im2 is leading Im1 by theta, or you can also say that Im1 is lagging Im2 by theta, right? Now the resultant of these two phasors, Im2 and Im1, which let us say represent the two sides of a parallelogram, which is OBCAO. So this is a parallelogram here. So OB and OA are two phasors which are representing two currents. I1, this is I2, sorry, this is I1 current. So their peak values are Im1 and Im2, right? So the resultant of these two phasors is IR, which is leading the first current by some 5 degrees, right? So if you extend it here like this and you draw a perpendicular, which is CD, so you can find out the resultant, which is OC, by using a Pythagoras theorem. So OC square is equal to, you have OD square plus CD square, right? So OD can be written as OA plus AD. It is OA plus AD, and OA is nothing but IM1 plus what is AD here? AD will be, this is base. So AD is equal to, it is equal to AC cos theta. This is theta, right? So O, this AC is nothing but this IM2. If you see, these are same. So it is OD is equal to Im1 plus Im2 cos theta. So we'll put it here and we have got this equation, this one. So we'll open all these and we'll get these equations on simplifying. So the resultant phasor or resultant vector, which is basically the addition of two vectors, two phasors basically, so is this one. So we can also obtain the value of phi, means the phase of resultant. Phi is nothing but the phase of resultant with respect to this reference Im1. So tan phi is equal to CD, this one, divided by OD. OD is OA plus AD, and we have this equation here. So if we have to find out the instantaneous value of this particular phasor, how we will write? This IR is the resultant, where capital I represents the static value or DC value basically, or the maximum value or magnitude of this quantity. So it is IR, which is equal to this peak value, which is IR, capital IR sine omega t plus phi. So plus phi we are taking with respect to this particular, right, reference. So this is how we can add two phasors, two alternating quantities, which are represented by some phasors. Similarly, we can subtract the phasors also. If we have to subtract, let us say there are two phasors, OA and OB, which are two phasors basically. So if I have to subtract these, so what I'll do, I'll backplot this OB phasors, right? We'll back plot this one, and then we'll have the resultant of these two. So this is OB, and this is minus this is minus OB basically, this one. So the resultant OC will be equal to OA minus OB, or it can be in this case, this one is OC is equal to OA minus OB. Now, if you can do the same thing with this one also, if you backplot this A, so this will become minus OA here, and the resultant would be like this. Okay. So this is, let us see. So in this case, like here, in this case, OC is equal to OB minus OA. So we can have any, we can use any one of these two. The ultimate magnitude will remain same. Okay, the magnitude of OC will remain same. So this is how we can add or subtract the alternating quantities which are represented with phasor. Okay, so in this lecture we have understood about phasor. Okay, so phasor is basically a rotating vector which is represented with a line and arrow, which is rotating in anticlockwise with some angular velocity omega, right? So uh, it, when it rotates with this speed in anticlockwise, it produces a sine wave. Okay, so alternating currents and voltage can be represented with the help of phasor. We can represent two alternating quantities also, which will show the lead and lag nature of the alternating quantities, lead or lag, right? So uh, we have also seen how two phasors can be added or subtracted with one another. So we have to remember while adding or subtracting that voltage can be added to a voltage. Okay, and current is added to current only, right? So we cannot add voltage with the current, no, right? So in our next lecture we will see how these phasors are represented with in rectangular form, in uh, polar form, how we represent a phasor with a complex number. So we will see one or two numericals also on this. So for this lecture, this is it. Thank you so much.